The question is, the donor and acceptor impurities in an abrupt junction silicon diode are 1 times 10 power 16 and 5 times 10 power 18 per centimeter cube respectively. So donor concentration, that is ND, is 1 times 10 power 16 per centimeter cube, and acceptor impurities, which is Na, is equal to 5 times 10 power 18 per centimeter cube. And then the intrinsic carrier concentration is given 1.5 times 10 power 10 at room temperature, and KT by Q, which is thermal voltage, is 26 millivolts, and permittivity of silicon is given, which is epsilon naught times epsilon R of silicon is given directly. And the question is the built-in potential and the depletion width. So the built-in potential and the depletion width of the diode under thermal equilibrium conditions. So this PN junction diode is in thermal equilibrium condition, respectively R. So we need to find the built-in potential first. So let's see that the built-in potential formula is given by KT over Q, which is thermal voltage, times ln of ND Na over Ni square. So if we write this, this is 0.026, this is 26 millivolts Vt, times ln of Nd is 10 power 16, Na is 5 times 10 power 18 divided by Ni square is 2.25 times 10 power 20. So this can be equated to or reduced to ln of 5 by 2.25 times 10 power 14. So we can find this value. This is, so 0.026 times ln of 5 times 10 power 14 divided by 2.25. This is 0.8589, which is approximately 0.8589 volts, which is approximately 0.86 volts. So we have found the VBI. So we have B and D options left. We need to find the depletion width now. So depletion width formula is given by depletion width under equilibrium is given by 2 epsilon naught epsilon R VBI over Q times 1 over Na plus 1 over Nd whole power half. So if you substitute the values here, the entire epsilon times epsilon R is given as 1.04 times 10 power minus 12 farad per centimeter. So let me write that. 2 times that is 2.04 times 10 power minus 12 farad per centimeter. Let's not forget the units here. Okay. When this is per centimeter, we have to make sure Na and Nd are also per centimeter. Of course they are. So that the entire depletion width at the end will become in centimeters. Okay. Times the built-in potential, which is 0.86 divided by Q 1.6 times 10 power minus 19 1 over Na. Na is 5 times 10 power 18. Now the order of magnitude for these two are 16 and 18. So I'll write it in the least one. So I'll write this as 500 times 10 power 16 plus, so that it will be easy to reduce, 1 over Nd. Nd is 1 times 10 power 16 whole power half. Let me reduce this and write. So this is 2.04 times 0.86 divided by 1.6. So I have 1.0965, this value, times 12. This becomes minus 7. So when I take it to the numerator, it becomes 10 power 7. Now if I reduce this expression, it will become 1 10 power 6 plus 500 10 power 6, 1 times 10 power 16 plus 500 times 10 power 16 plus becomes 501. So I have 501 times 10 power 16 divided by 500 times 10 power 32. Hence I will have 1 over 10 power 16, because 1 10 power 16 gets cancelled, whole power half, and the units will be in centimeters. So if I reduce this expression, so 7, and it becomes 9. Okay, let me multiply this value times 501 divided by 500. This is 1.098. Okay, times 10 power minus 9 whole power half centimeters. Now to reduce this, I will make it in terms of 10 power minus 10, so that I shift this decimal here. So it becomes square root of 10.98 times, if I take 10 power minus 10 out of the square root, I get this 10 power minus 5 centimeters. Let's find this value. Square root of 10.98, which is 3.3 times 10 power minus 5 centimeters. So this is the depletion width of the p-n junction under equilibrium. So the answer is option D.